Hello everyone. We have already started discussion related to different fabrication techniques. We have seen thermal deposition technique and different kinds of physical vapor deposition techniques, and broadly they are classified in thermal, E-beam and then sputtering. So, these are the three different techniques that are widely used in physical vapor deposition. We also have seen what is a thermal deposition technique, where you have a chamber, vacuum chamber, then you keep your source material somewhere here and then you apply say high current so that you can generate heat here, and there is a substrate kept on top. Once this is heated, they will start evaporating, and this evaporated material will condense on the substrate and they will create a film of the source material on the substrate. This is typically what a thermal deposition technique is, but there are different heating techniques available in case of thermal deposition. We also have briefly discussed the same. The first one is the filament coil heating, where you have an coil, heating coil, and then you put the source material inside. But this process is simple and inexpensive, but the problem is if the heat is very high, you may find that the coil material is also getting evaporated and then getting deposited on top of the substrate. So, it may create certain sort of contamination. There is a risk of contamination. Then we also have inductive heating process, where you use a crucible. So, in this case it is made of boron nitride, and then you have inductive coil across it. Now, because of this eddy current, they will also create different heat and evaporation, but in this case also there is a risk of contamination, because if the heat is very high, you may find that crucible material is also getting evaporated or coil material is also getting evaporated, and then these materials may contaminate the thin film that you wish to create on a substrate. To overcome that, I won't say it's to overcome that, that's a separate process altogether. There is a process where, other than using heat from coil, inductive or resistive coil, one can also focus heat on top of the source material only using a focused beam of electron. So, what they do is, in this case they have a source of electron, say a filament, and then they use the electron beam in order to heat the source material. So, in this case the crucible or say any other filament is not getting heated, rather the source material is also only getting heated and the source material is only evaporating. So, the risk of contamination in this case is much lower, because it takes help of electron beam. We call it E-beam evaporation. So, the E-beam evaporation technique is also similar to other physical vapor deposition technique, where you have a substrate, source is evaporating and then getting deposited on the substrate. The basic principle is still same, just the source of heating is different. It also can you can have a thin film of 5 nanometer to 300 nanometer using this technique. So, it has two major components. One is the electron beam or the source of electron beam, and another one is the crucible, where you keep the source material. So, electron beam is well confined and focused, as we have seen, because this process is also a high vacuum process. So you have to put the entire system inside a vacuum chamber. You'll have an electron beam source and will have a crucible, and then electron beam is also very focused to that particular material only. Then different material can be rotated and placed under the beam, which is a very big advantage of this process. So what I mean by that is, if you have an electron beam over here and say you have a disc where different materials are kept at different crucible, you can rotate that disc and put some other material just beneath the electron beam, so that that material can also get deposited, which is not that simple in case of thermal, because in case of thermal, in that case either you need various heat source, and if it's a single heat source, then it will heat all the materials, it will create contamination. So we'll discuss this maybe in the next slide. Then this also allows, because it has this advantage of keeping multiple material inside the chamber, this allows deposition of multiple materials subsequently without disturbing the vacuum. So you don't need to disturb the vacuum. Once you have set all the system inside the vacuum chamber, you just externally make an arrangement where you can rotate the disc where source materials are kept, put that disc under the electron beam, material A will get deposited, then you rotate it, put the second material B beneath the electron beam, material B will get deposited. So you can deposit multiple material one after another sequentially. So it can create multi-layer multi-layer thin films. So which is a advantage of e-beam evaporation. Now this is something is like a schematic representation of e-beam process where you have magnets. These magnets will help to focus the electron beam to the crucible, and then you have a filament which is the source of the electron beam. And this is a image of an e-beam process where this is the chamber. You have a system also where you can fit or decide the recipe of certain deposition, and then you can also keep an rotatable multiple crucibles where all these crucible will have different materials, say A, B, C, D, something like that. Now the advantage of that I already have said. For example, if you have an electron beam, this is the filament, this is the electron beam focused on material A, now will deposit say material A on this substrate. Now if you want to deposit material B, what you do is you rotate this disc and then put say material D underneath this electron beam, then material D will get deposited, and so on and so forth. So you can very easily create multi-layer structure of multi-layered thin film of different materials, say A, B, C, D, right. This is not possible in thermal deposition, because if you heat this material, the heat will also propagate to say material C or material B to some extent, then they will also start evaporating. So you will find that there will be a lot of contamination. You will not get a sequential deposition, rather all materials will mix together and will start getting deposited, and there will be no control over it. So it's very important that if you want a sequential deposition and thermal evaporation system, you vent or break the vacuum, take the source material out, put a new source material, again do the vacuum, again start deposition. So it's a like lengthy process, time consuming process, and one of the major problem is, for example, when you start a deposition, say if this is the vacuum chamber, and once you start deposition say of material A also will get deposited on the walls, right. Now in the same, if you put material B, and if the heat is quite high, this may also heat up the material deposited here nearby, and they also may get deposited. So there is a risk of contamination as well. However, in this case, in case of e-beam, because your heat source is very focused to that material, the chance of contamination is very less. So, multi-layer deposition, if one wish to conduct, it's better you do with an e-beam evaporation technique. Then the filament usually goes up to 2500 degrees centigrade with an electric current, and multi-layer deposition is possible using this technique, provided you have this rotatory disc option available there. Then the next process is like sputtering. Sputtering again is a vacuum process. So briefly, if I discuss the sputtering technique, it's the same as what we have discussed. The basic principle is same. You have a source material, you heat it up, it will get evaporated and deposited, as we have seen in e-beam and thermal. But in this case, rather than source, we call it a target. So what you do is you keep a target material as it is shown over here. Then there will be some energized molecule which will hit that target material. They will knock out some of the target material molecules or atoms. They will go and get deposited on the substrate. This is what the sputtering technique is all about. So this is similar to what the e-beam and thermal process does, but in this case, rather than a source of heat, what we do is we put a low concentration argon inside the vacuum chamber, and then we create a plasma. Plasma, what is a plasma? Plasma is a different state of matter. I am not going in details of that plasma. You have solid, liquid, gas, and then you have plasma. So plasma is like a combination of different energized molecules. So what they do is, once argon is there, they'll create argon plus, they'll take out one electron. Because of that high energy, one electron will come out of argon, it will create an argon plus ion. Then what they do is they put the target material into a negative potential. Because this is negative in nature, this argon plus the argon plus atoms will hit the target. Because they are energized, argon plus is energized, while they are hitting, if they have enough energy, they will knock out some of the target material atoms or molecules, and these atoms or molecules will then go and get deposited on the substrate. So usually we create a very high vacuum in this case, and there will be a small amount of argon gas because we need a plasma in this case, and then we apply high negative potential in the target so that this argon plus can hit the target material very hard, or they can transfer the energy to that target material so that we can get target materials atoms that are coming out from the target and getting deposited on the substrate. So this is the sputtering technique. However, in this process, one has to also take care of the recipe. What should be the potential of the target, what should be the time, what should be based on the target. You also should optimize different other parameters like the potential and time, so that we get a nice deposition of the source material on the substrate. So we have started discussing on sputtering, and we have seen what is the basic mechanism of sputtering, and we have discussed that in sputtering we have some certain sort of gas inside a vacuum chamber. It's not exactly, because you have certain sort of gas, it's not completely vacuum. So you put a gas inside, and then what you do is you create a plasma, and then the energized atoms, here it is shown as red atoms, that hits the target, and then the material that you want to deposit starts depositing on the substrate. Now in this case, what you can do is you can apply a high voltage DC voltage in order to create the plasma inside the chamber, and then that plasma will interact with the target, and then materials will get deposited. This process is uh, known as sputtering, and in this sputtering process you'll be able to deposit different types of materials on a substrate. This is the basic mechanism. In case of DC sputtering, we use DC voltage, in fact, high voltage of DC, in order to create the plasma inside the chamber. And similarly, in order to make the process more efficient to some extent, what we do is we apply magnetic field inside that box near the target. So in that case, if you have magnetic field lines present, for example, say you have one magnet here, another here, and here, based on the pole of this magnet, you'll find that there are magnetic fields from one magnet to the other. So you'll find a lot of magnetic fields near the target, and this magnetic field actually helps the generated electrons to float in a longer trajectories. So the electrons that are generated inside the chamber will now float in a longer trajectory, and then they have high probability of ionization because they'll hit more number of atoms because it's more or less near the target, and in that way they'll create a lot of ionized atoms in the plasma. And once you have more number of ionized atom, you'll have higher sputter rates. And secondly, because there is a magnetic field present near the target, this magnetic field also will help to focus the ionized atoms towards the target. So it will also increase the focus of these atoms. So in this case, you have two different advantages. One is higher probability of ionization, which leads to higher sputter rates. And then because of this magnetic field, you have a better focus of these atoms towards the target. And because we use magnetic field in this case, we call it magnetron sputtering. So this is another type of sputtering where the applied power creates the plasma, but at the same time you use magnetic field in order to make it more efficient to some extent. This is known as magnetron sputtering. Now, based on the power that you use for plasma creation, we also can classify the sputtering process into DC sputtering and RF sputtering. If you are applying DC voltage in order to create the plasma inside the chamber, then we call it DC sputtering. In this case, you have a target which is cathode, you have a substrate which is anode. Between cathode and anode, you apply high voltage of DC, and that in turn will generate a plasma. So we call it DC sputtering process. Similarly, you also can apply RF power in order to generate the plasma. However, the sputtering process remains as it is, I mean, as we have discussed, but the generation of plasma depends on the RF power, and the frequency that usually we use in case of RF sputtering is 13.56 megahertz, which is more or less fixed because it is decided to have this frequency so that the sputtering process do not interfere with any other type of electronic gadgets and etc. We use lot of electronic gadgets and lot of communication devices, so it's very important that we use a fixed RF signal in this case in order to create the plasma. So here the source of the plasma, or the source that is responsible to create the plasma, is RF. That's why it is called RF sputtering. So we have DC sputtering, we have RF sputtering.
Now if the magnetron effect is there, then we can call it RF magnetron sputtering, DC magnetron sputtering. Okay, so that is how we can classify sputtering processes. Now the RF sputtering process has advantages as well as disadvantages. The advantages are listed over here. So RF sputtering process actually uh, has various advantages. For example, the first one is high plasma. That means the plasma can extend in vacuum chamber and not limited to the target. Okay, so if you have RF sputtering, the plasma can extend to the vacuum chamber inside the vacuum in the vacuum chamber as well. The process is comparatively low pressure, so the plasma can be maintained in low pressure. The typical pressure range is given over here. High sputtering yield. Magnetic field in magnetron can trap more electron at lower pressure. That's why the sputtering yield is comparatively higher. Uniform layer deposition, because it eliminates charge built on the cathode surface. This particular process eliminates the charges that build on the cathode surface. Hence, uniform layer deposition is possible. In this case, larger target surface is involved in sputtering process usually. So these are the advantages. However, it has some disadvantages as well. It has a heating effect associated with it. Higher voltage is needed for high sputtering rate, so it may create heat in the chamber. Then complicated and expensive. The entire process is a bit complicated because you have to attach an RF power source there, so the process becomes a bit complicated, and also it is expensive compared to DC. Special connectors and cables are needed because for RF, a special connector and cable is needed. Normal cables and connectors is not sufficient. Then deposition rate is comparatively lower at a particular power. So in this case, the deposition rate is lower at certain power. If you consider a fixed power, then in case of sputtering, RF sputtering, you may find the deposition rate is comparatively lower. So these are the advantages and disadvantages of RF sputtering. So this is more or less what are the different types of sputtering processes. This will give you an idea about the sputtering technique and what are the basic details associated with the same.
Now there are three take home messages. The first one is e-beams are also used for deposition. As we have seen, in thermal you have thermal source, heat source, be it a resistive, be it an inductive, and then there are different heating techniques for thermal depositions, as we have seen. But in case of e-beam, you use e-beam, focused e-beam to heat source materials for deposition. Then in case of sputtering, you use argon atoms as energized atoms or argon plasma to create these energized atom in order to create, or in order to make this deposition possible, because this energized argon atom will anyways hit the target and then they will knock out some of the atoms and that will get deposited on the substrate. So this is more or less the sputtering technique. So in upcoming discussion, we will see some of the other deposition techniques. Till then, thank you.